Hello, this is Dr. Jabbour, and today I'm going to go over atoms and elements. So this is more of an introductory lecture to basic chemistry for biology. So think of matter, the word matter is anything that takes up space and has mass, and it's made of elements. And elements, think of elements as the little Lego pieces that you put together to form matter, right? So if we're building, well, we're going to talk about cells and then tissues and organ systems. All of this is made of something very, very small that you have to assemble together to make it bigger and bigger. So we just happen to be able to see at the tissue level and organ level. We can see that with our, at the naked eye, but really microscopically, we first have cells that come together to form the tissues, to form the organs, etc. Now, um, even to form a cell, you need even smaller structures, and it starts with the elements. Elements are your smallest Lego pieces that you're going to assemble to make things, to make matter. So element is a substance that cannot be broken down to other substances by chemical reactions. So it's really the smallest that we can go as far as little Lego piece. Now, elements are made of atoms. So you will have what we call one element, and it is made of kind of several different atoms within that element. And this is something that takes a while to kind of like, understand the difference between atoms and elements, and people kind of use one word and or the other kind of, interchangeably. But I'm going to give you a very specific example. If we just look at carbon, carbon is what makes up organic matter. So it's in our food, it's in our wooden table, it's really in everything almost. So carbon, we have what's called a carbon 12, and we have what's called a carbon 14, and we have, other different kinds of carbon. So I think there's a 16, maybe there's a 10. I forgot the different kinds of carbon, but these are different kinds of carbon. They're all carbon, the atom of carbon, but because they have slightly different atomic mass, and we're going to talk about atomic mass in a little bit. So they vary in their physical properties. So carbon 12 is your most common carbon that you find everywhere. And carbon 14 is your radioactive carbon. It's a carbon that actually emits radioactive waves. So they're a little bit different from each other, these different carbon atoms, but they're all in the element called carbon. You see the difference? So the element is a group of all um, uh, of all different atoms that are of all the same element, the carbon element here. Okay. So we speak of elements as more of in general, the element of carbon. Sometimes if we just say the atom of carbon, we're basically implying carbon 12 because that's the carbon that's in our food and in everything. So for human beings, we need, as human beings, we have 25 essential elements that we need for life. So you need to know those, and especially the 4 elements that make up 96% of what we need are oxygen, carbon, hydrogen, and nitrogen. You have to know at least those 4. These are the 4 most important elements that the human being needs to survive. Oxygen, because of course that's the only way we can still breathe and produce energy. We need oxygen. Carbon, hydrogen, nitrogen, those are just very, very important parts of our body. So those are the four most essential. But in total, there's 25 because we also need calcium, we need phosphorus, we need potassium, and sodium and sulfur and magnesium and chlorine, and also trace elements that are very, very small in percentage, but we still need them to survive. So in the future, when in a more upper level biology course, when you learn about the um, the way cells talk to each other, for example, two neurons in the brain talking to each other. So we call this a synaptic transmission, or when a neuron in your brain talks to a muscle cell, so it contracts, it gives it an order to contract. So these communication between the cells, they require calcium, they require sodium ions and potassium ions. So it's important for life, even though their percentages is not as abundant, but they're still important. So we would be in a lot of trouble if we didn't have these in the right percentage, even though it's a small percentage. So the foremost: oxygen, carbon, hydrogen, nitrogen. So this would be a typical test questions. All of the following are the, the four most abundant ones, or the ones that are the most needed by the human body, except, so you'd have a list of 5. Of course, you would have oxygen, carbon, hydrogen, nitrogen, and maybe, sulfur. So you would have to recognize sulfur is not part of those 4 most needed. But it's part of the 25. Okay. All right. So the element is the smallest, but like my analogy, it's the smallest Lego piece. Okay. So these different elements, so the element of carbon, or the element of nitrogen, or the element of oxygen, they each have different properties, right? A carbon element is not the same as oxygen, is not the same as nitrogen. And these properties are due to their subatomic particles. So the little particles that make up the element, they are different between oxygen, carbon, nitrogen. They're different. So now let's look at what are these subatomic particles. So if you separated these subatomic particles, you wouldn't have an element anymore. And that's why we say it just doesn't exist anymore. There's no more physical properties. They have to be, these 3 types of subatomic particles have to be together in a specific number, and that would create that particular element, or another, or another. So an element is made of different atoms within it, but that's what we just talked about. And then different elements can make up compounds or molecules. And that's actually the subject of the next chapter. But each element, so that's what I'm trying to focus on, each element is made of one kind of atom. So for example, the element of carbon, it's all carbon, it's the carbon atom, but there's slightly variation between these carbon atoms, like carbon 12 and carbon 14 and carbon 16. So let's see what's the differences. So every atom is made of 3 subatomic particles: protons, electrons, and neutrons. 2 of them have charges, protons and electrons, and one of them is actually a neutral subatomic particle. So subatomic means it's even smaller than the atom. So these 3 subatomic particles, they come together to make the atom. So protons, they're illustrated in pink here. Protons happen to be positively charged. So there's a little plus sign over here. Neutrons happen to be neutral. They don't have a charge to them. And both of these together are in the center of the atom, in what we call the nucleus. So the nucleus, that's a term that we use for basically the center of something. So the nucleus here is the nucleus of the atom houses protons and neutrons. Okay. And electrons are negatively charged. So we have a little negative sign over here. You can see that. And these electrons, they're not in the nucleus with the other two. The electrons are orbiting, or we say gravitating, or they're orbiting around the nucleus like that. And we're going to talk about different orbits or different clouds, electron clouds, because they're actually, the more they are, the more electrons we have, the more organized it is. It's very organized on how they are actually flying around the nucleus. It's not disorganized. It's very, very specific, and we're going to get to that. All right, so 3 subatomic particles, 2 in the center, and 1 flying around the nucleus. Okay. So the atom is the smallest unit of matter that retains the properties of an element, and it's made of subatomic particles. If you separate these subatomic particles, you have nothing left. Okay. So each atom has its specific atomic number and its specific atomic mass. And we usually write them. So I'm going to use carbon as the example. So carbon, oops, let me go back to a darker color. Carbon, and I'm going to use carbon 12, not carbon 14 or carbon 16 or 10, carbon 12. So carbon 12 there's 2 specific numbers that we use for every atom. We have the atomic number and the atomic mass. So the atomic number, what is that? The atomic number, when you see an atomic number, when you're given an atomic number for a specific atom, this tells you how many protons, it's the number of protons that are in the nucleus of that atom. So that tells you the number of positively charged that are in the center of that atom. And because atoms are considered overall electrically neutral, if you're told that they are 6, in this case, in this example, 6 protons, you can assume that they are 6 electrons. So even though that number is specifically for the number of protons, you can, here, this is like a deduction. Yeah, you're assuming here, because you're given the number of protons, you're going to assume, because the rule is atoms are overall electrically neutral. So if you have 6 positive charges in the center, you must have 6 negative charges flying around. So that number 6 tells you 2 things, the number of protons and the number of electrons for that atom. Okay. The atomic mass is that second number, which is, usually bigger. The atomic mass, the atomic mass, it's the number of protons plus neutrons. So 12 is the sum of the protons and neutrons, and remember, they're both in the nucleus. So, and that's really the mass of the atom. The electrons that are gravitating around, that are orbiting around the nucleus, they're very, very light. So we really don't consider them or add them in the weight. We use the term mass, in the mass of the atom. We only consider protons and neutrons for that mass. So knowing that the atomic number is 12 for carbon in this particular example, 12 is the number of protons plus neutron, and knowing that we happen to have 6 protons for this particular atom, carbon, this automatically, this number here, 12, gives us, so this is this conclusion here, this little arrow here means, oh, I'm concluding that because I know there are 6 protons and the total here is 12, that means the neutrons must be in the number 6, right? 6 protons plus 6 neutrons together makes 12, That's the atomic mass I was given. Okay, so there must be 6 neutrons in this particular atom. Great. So now we have all the information for carbon 12. We know that it has 6 protons in the center, it has 6 neutrons as well, and it has 6 electrons flying around. 6 and 6 and 6. Okay. Now let's look at one more definition, the definition of isotopes. So that's within that same element, we have what we call isotopes, which means that each carbon in that element has a slightly different physical property. And I'm going to go back to using carbon. So in the element of carbon, go back to this color. In the element of carbon, we have carbon 12, we have the atom carbon 14, maybe we have carbon 10, carbon 16, we have different other kinds. I don't know the other different kinds. I'm just gonna pretend there's a carbon 10. But carbon 12 is your carbon that's in everything. And carbon 14, I told you earlier, that's the one that has some radioactivity that comes out of it. So all of these are carbon. So they're all part of that one element called carbon, the element of carbon. But each one of these, carbon 12, carbon 14, carbon 10, these are different atoms of carbon, right? They're different because one has an atomic mass of 12, one has an atomic mass of 14, and the third example here was 10. So what's the difference between carbon 12 and carbon 14? Well, let me tell you one more thing about these isotopes. They all have the same number of protons. So that atomic number over here is all the same. See? That's the atomic number. And it's the number of protons, right? This is what we call the atomic number. That hashtag is number. The atomic number is the number of protons, and they're all the same. So isotopes have the same number of protons. What's different between them is the number of neutrons. If they have all the same number of protons, so that 12 came from the sum of 6 plus 6. The 14 came from the sum of 6 plus, let's write it out. So this was 6 plus 6. And this was 14 is 6 plus 8. Because to get to 14, you don't need, you don't need 6, you need 8 neutrons. And 10, it would be 6 protons, but only 4 neutrons to get to 10. So these different carbon isotopes, all of these isotopes of carbon, they're all the same number of protons. They all have the same atomic number, but what's different between them is the number of neutrons, and that will change their physical properties and give them different physical properties. Even though they're all carbon, atoms of different atoms of carbon within the same element of carbon, they all have slightly different physical properties. Okay, so that's the summary of the 3 subatomic particles that make up an atom: protons, neutrons, and electrons. Protons and neutrons together are found in the center, which we call the nucleus. That's the center of the atom. Protons are positive. Neutrons are neutral. And together, they make up the atomic mass. So because each proton is considered to have the equivalent of 1 atomic mass unit, neutrons, each one is 1 atomic mass unit. So for every single one, we have 1 more unit, 1 more unit. So you just add them up and you end up with the mass of the atom. Electrons are so light that we don't count them. They're negligible. and they're the ones flying around the nucleus, and they happen to be negative. Okay. So here's the periodic table of all the elements that we know. And there's around 92 naturally occurring elements in nature that are found in the ground, in, I mean, um, uh, where's cobalt? Because there it is, cobalt. Cobalt is being dug in the ground. Um, and it's being mined so to be used in your cell phones, and all these elements are found as they're in their some of them are rare resources in the ground, and others are very, very abundant. Some are in the form of gas like oxygen, and some are in the form of solid like carbon. So they all have different properties, they all have different abundances in nature. And the way that they are all laid out in this periodic table, we call this a periodic table, is very specific. I'll give you some indication of how they're organized. If this was a more advanced chemistry course, I would definitely get into like the details of all of this, but we don't need to know all of the details. But here's carbon, the one that I've been using so far. You see this? There's carbon right here. Carbon. You can see the atomic number over here. You can see the atomic mass over here. So they're in this particular design, they have them kind of like side by side. But when you write just the atom by itself, the atomic mass is at the bottom and the atomic number is at the top. Okay. Next to it is nitrogen, oxygen, hydrogen is over here. What else can I say for now? That's all I'm going to say for now. So how are they kind of organized? The vertical columns are called groups, right? So every column, so here, this is a group, this is another group, this is another group, right? So every column is a specific group. Elements have similar physical and chemical properties to each other within that group. So they basically behave the same in general. Within that group. And really that's due to the fact that they have the same number of electrons in their valence shell. That's something I haven't talked about yet that I'm going to kind of talk about in a minute. And that has to do with how all of these electrons are distributed along these orbits. So I'm going to talk about these different orbits and what does that mean to have a valence shell? What is the valence shell? So the rows are called periods. So if we're looking at a row like this this is a row, this is another row, this is another row, right? So each row, all the elements in a period, is called a period. The rows are called a period. All the elements in a period have the same number of atomic orbitals. So these are basically the different levels of electrons that are kind of flying around the nucleus, either closest to the nucleus, a little bit further away from the nucleus, etc. Yeah, so I'm gonna get to that in a second. So I just want to show you a little bit more about the periodic table and its outer limits. So this periodic table, this is like, really kind of elements that are just either brand new. The new elements are number 113, 115, 117, 118. They don't even have a name yet because we just discovered them. I don't have dates either. I don't know when that was. So we're still discovering new elements, in the ground that we didn't even know existed, and how they can be, what are their physical properties. So we're still studying them. And this particular diagram here also shows you, for example, where uranium sits. Uranium, that Uranium is what we use to make a radioactive substance. That's the heaviest natural element known. And neptunium happens to be the first element that was actually made artificially in a lab. Just I would never ask about that in an exam. I just wanted to kind of just give you a little bit of knowledge on that this is not set in stone. It's still evolving. We're still discovering new elements. So we're going to practice with an example, and the example is helium. The example on the next slide, it's helium. And if you look at in the periodic table, helium has an atomic number of 2 and an atomic mass of 4. Oh, by the way, I forgot to tell you, you see that the atomic masses are not just a round number like 12 and 14 and 16 and it's 12.011 or 14.007. So this is not like a full round number, because within each element we have different atoms. So if you go back to the example of carbon, we had carbon, let's say 10, carbon 12, carbon 14. They each have slightly different properties. I told you carbon 14 is radioactive. Carbon 12 is not. It's the regular carbon in all of our food. So the average of all of these atomic masses comes down to 12.011. That's why we see a decimal number and not a round number. We don't see 12, we see 12.011. Or for nitrogen, we don't see 14, we see 14.007. It just happens to be the average of all of these different types of carbon atoms within that carbon element. Okay, I just wanted to say that. So in the future, when I just pick an example, I just round the number, of course, and it's usually the most abundant atom within that element that the round number comes to. So for carbon, it would be carbon 12. So for helium, atomic mass is 4, atomic number is 2. There we go. There's the atomic number, and there's the atomic mass. So that's the number of protons, if you remember, the number of protons. And here it's 2. What does that tell you, though? Because what additional information does that tell you? Look at this. Because an atom is overall electrically neutral, if you are given the number of positive charges, you can assume we have the same number of negative charges. So if you're told helium has 2 protons in the center, in the nucleus, in the center of the atom, there's 2 protons, you can then assume that the number of electrons is also 2. That's what that means. That's what that means. So you know that there are 2 electrons that are flying around the nucleus. Okay? The atomic mass here being 4. Here, atomic mass is the atomic mass is the number of protons plus the number of neutrons. And here you are told it's 4. Well, you already know the number of protons. The number of protons, the atomic number told you what it was. It was 2. And 2 plus something is equal to 4. So now, because you're told what the atomic mass is, then you can basically deduct that number of neutrons is 2. 2 plus 2 equal 4. Perfect. Now we have all the information. We know that there are 2 protons in the center, 2 neutrons with them in the center, and 2 electrons that are orbiting around the center. That's it. And we can do that with all of these other ones. So I'm actually going to take oxygen. So before looking at all of this, I'm going to take one more example that I'm going to break out break down for you, and that will give me a chance to talk about the valence shells. Is it? Yeah, let's do that now. So I'm going to use the example of oxygen. And you see here, atomic number is 8. You see that? 8. And atomic mass is 15.999. I'm going to say 16, okay? So for oxygen, it's 8 and 16. So let's do that. I'm going to add a little drawing page right after for oxygen. So oxygen is 8 and 16. By the way, I didn't say that, you know, those letters are basically the symbol of each one of these elements. So O for oxygen. Okay, so let's kind of break it down. 8 atomic, this is the atomic number. And this is the number of protons. So you have 8 protons. And because we know that atoms are overall electrically neutral, we can infer that electrons, there must be 8 of them as well. 8 plus charges, that means we have 8 negative charges flying around. Okay, and the atomic mass is equal to the number of protons plus the number of neutrons equal to 16. Because we know the number of protons is 8, so the number of neutrons must be 16, take away 8, and now you have 8. And that's equal to 16. And there we go. We figured out the number of neutrons. So that's it. We have the information for oxygen. We have 8 protons in the center. So when I say 8, there's 8 of these. 8. But I'm just not drawing all 8 of them. I'm just drawing the number 8. And let's do it in brown. So 8, oops. It's not protons. 8 neutrons. Okay, that's not a very... 8 neutrons in the nucleus, okay, and 8 protons in the nucleus, and 8 electrons that are flying around the nucleus. Okay, that's it. 8, 8, 8. We just kind of deducted that from the numbers that were given, 8 and 16. So now let's talk about those 8 electrons, because this is where I want to concentrate now on. So I'm going to draw the levels, the different orbits that the electrons can be in. So right here, I only drew kind of one dotted line showing the electrons are going around and around. Actually, they're not all going around and around together on the same level. With the nucleus being in the center here, so I'm just going to write nucleus down here without writing protons and neutrons. With the nucleus down here, you have different orbits outside of the nucleus. You have the one closest to the nucleus, and the next one, and the next one, and the next one. And there is a specific order of filling. What does that mean? That means you can only have 2 maximum electrons in the first We call them shells. In the first shell. We call them a shell instead of calling them orbits, but that's just how we call them. And so it's a shell around the nucleus, and the one the closest to the nucleus is called, well, they're all called shells. So there's one closest to the nucleus. The one closest to the nucleus can only take up 2 electrons. That's it. If there are more electrons to that particular atom, they have to go to the next shell. So for oxygen, if we put the first 2 electrons in the first shell, how many electrons are we going to be left with? 8, take away 2, and then that's 6. So we have 6 electrons in the second shell. And the second shell has the capacity of taking a maximum of 8. The first shell happened to be a maximum of 2, but that's it. The other shells around the nucleus, they're actually able to take on more electrons in each one of them, up to 8. So if you have 6 electrons left, then there's room for all 6 to be on that shell, which means that for oxygen, only for oxygen, there's actually no third shell because we don't need it. There's no electrons out there. All the electrons, the leftover electrons, are on the second shell, and that's it. So for oxygen, there are only 2 shells with 2 electrons on the first shell and 6 electrons on the second shell. Okay. So now you heard about shells. The last shell that is filled with an electron, so here, let's say I'm drawing 2 of them. Right, the first one and second one. The last one filled is called the valence shell. Valence shell is the last one filled. Last one filled. So for oxygen, we didn't have a third one. It just doesn't exist because we only need 2. So the second shell happens to be the valence shell for oxygen. Now, with another atom, it could be different. I'm going to do another example. I'm going to do sodium. And sodium is right here. Look at sodium. It has an atomic number of 11 and atomic mass of 22. So let's do sodium on its own page. That way you kind of start getting the feel for what we're doing here. So what did I say? 11 and 22, if I remember correctly. Okay, so 11, that means we have 11 protons, which means that it's the same as saying we have 11 electrons, because atoms are overall electrically neutral. If you have 11 positive charges, that must mean you have 11 negative charges orbiting around. Okay, and here we have number of protons plus neutrons equal 22. That's the atomic mass, right? This is the atomic mass. This is the atomic number. The atomic mass is number of protons plus neutrons equal here, in this case, 22. We already know that we have 11 protons. What does that mean for neutrons? Well, it must mean we have also 11 neutrons to make it equal to 22. Okay? All right. So now we have that solved, and this is kind of the typical little exercises that you'll have to like solve for like a quiz or a test. Let's look at the electrons now. 11 electrons. What are we going to do with them? Well, let's draw the shells and see how many do we need to fill? Do we need to, what are we going to do? So 11. So let's put 2 on the first shell and we fill it up. Okay. 11, take away 2. That means we still have, you can pause the video, you can think and do your own calculations. We have 9 left. 9, 10, 11. So 9. Can we really put 9 here? Remember, I told you it's a maximum of 8. It was a maximum of 2 on the first shell, and it's a maximum of 8 on the second shell. So we actually cannot put all 9 here. The 9 left over, we can't. We can put 8 of them here, and then you have 1 lonely electron on the third shell. So the third shell can take maximum 8. From now on, it's maximum 8. Second, third, fourth, maximum 8. But we don't have 8. We only have 1. Right? We only have 1 left. 2 plus 8 is 10. But we have 11 electrons, so there's 1 more. What do we do with it? We have to tell him to go up there on the third shell and just kind of fly around by yourself up there, because that's the rule. We cannot put you with those 8, and not with those 2, and not with those 8. So for sodium, we have 1 lonely electron flying all by itself out there. So let me give you another rule here. And this is something we will kind of dive more into when we look at molecules and salts and stuff like that. So in the next chapter, an atom will want to be stable. And to be stable, it needs to have a filled valence shell. So for stability requires a full valence shell. So what's a valence shell? It's the last shell filled up. We need to fill up whatever shell we are leaving with some electrons. It needs to be full. So what do? We can, here we have 1. And to fill this valence shell, we have to add 1, 2, 3, 4, 5, 6, 7 electrons from somewhere to make this atom happy and stable. That's kind of a lot of work. Like, where are we going to go get 7 electrons from somewhere? It's almost too much. There's another option, is the other option is to take this electron and get rid of it. And if you get rid of 1 electron, what are you left with? This shell is empty, which means we don't count it anymore. And you're down to the shell number 2. It's full. It's the outermost shell now, because there is no more 1 lonely electron. We plucked it off. So here we have this outermost shell. It's full. That's it. It's stable. Sodium is stable, the most stable. So sodium is most stable when it loses 1 electron. So when it loses 1 electron, it's going to end up with only 10 electrons left. Only 10 electrons left, because it loses an electron, right? That electron gets plucked off. In the next chapter, I'm going to tell you where that electron goes and what happens to it. But right now, we just know that it's getting plucked off. I like things neat, neat, neat. Okay, so 10 electrons. 10 electrons, that means we have 10 negative charges. We still have 11 positive charges in the nucleus. So this particular atom will have a tendency to become positively charged. Because by plucking an electron out, we are not making it neutral anymore. We don't have as many negative and positive charges anymore. We actually have more positive charges because we didn't touch those in the center. So we have more positive charges than we have negative charges. And that's why we write it like this. Once we're talking about the atom that's actually, out in, out of the periodic table, when we're talking about sodium atom that's in the with the actual sodium atom, how it's actually behaving, it loses an electron and becomes a positively charged ion. That's what an ion is. It's an atom that has either lost or gained an electron. In this particular example, sodium atom lost an electron and became a positively charged ion. We also call this a cation. And negatively charged ions will be called anion, anions, or anion. But we'll talk about, I'll give you another example of ion, a negatively charged ion, in the next chapter. I just want to explain the valence shell and those shells and the rule of how we fill these shells in here. Okay, so there we go. So in this particular diagram, you get to see the one lonely electron of hydrogen basically is in that first shell, and that first shell is not full. So for hydrogen, it's going to have a tendency to want to steal somebody's electron to fulfill its own valence shell, which is just one shell. There's just one shell for hydrogen. It has only one electron that goes on the first shell, and the first shell can take up maximum of 2. So this is not stable and wants to pluck off one electron from somewhere, or we'll talk about how atoms share electrons in the next chapter. So you see how every row is basically what we call a period. Every period represents the next shell and the next shell and the next shell. So the second shell, lithium happens to have 1 electron. Beryllium happens to have 2 electrons. You see it here and here. Boron has 3. 1, 2, 3. Carbon has 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. Neon has 8. So all of these gases that are in the last column, they all have a full valence shell. So they're very, very stable. Those gases at the end are very, very stable. The atoms that are before that, they require the gaining or losing of an electron from somewhere. So this is the same story for if we have more electrons and we're distributing it across even more shells. So here there's a third shell for the example of sodium element, more specifically sodium atom with the atomic, sodium atom, well, we don't care about what atomic mass, but the atomic number 11, when we distribute those electrons, you end up with one lonely electron on a valence shell. So it's going to have a tendency to want to pluck it off. But look over here. Chlorine, 1, 2, 3, 4, 5, 6, 7. Chlorine, and this is actually the little assignment worksheet that I can share with you, that I have shared with you. So do for your practice, do chlorine, atomic number 17, that means 17 protons, 17 electrons. Distribute the 17 electrons across these different shells and see what you have. So you're going to see that on the last shell, the valence shell has 7 electrons. So either we kind of ditch those 7, or what would be easier is to kind of gain one from somewhere. I wonder where chlorine's going to gain an electron from. I wonder. Okay. All right, so moving on, elements with the same number of protons. Oh, yes, I forgot to move this slide to a little bit sooner because we already talked about isotopes. I should have moved this slide sooner. I already talked about isotopes. They have the same number of protons, different number of neutrons, blah, blah, blah. They emit radiation, some of them. So a radioisotope is an unstable isotope. So the carbon and its isotopes. So carbon-12 is the most naturally occurring one. 98% of the carbon on Earth is carbon-12, I'm sorry. And carbon-13 represents 1%. And there's really overall 15 different carbons isotopes with even smaller percentages. Carbon-14 happens to be the radioisotopic carbon, and this is found in really trace amount, meaning 0.00000000001%. So 1 part per trillion, and it's used to date artifacts that have carbon in them. Because we know the half-life of a radioisotope and the half-life of carbon-14, what it is. When we measure the carbon-14 emission from a very old artifact, depending on how low that emission is, and because we know what's the half-life of it, we know if it's past half-life or not, and we can actually date that artifact. It's really fascinating. Okay. So 2 or more elements can combine in a fixed ratio to form a compound. Now we're going to bring these atoms together to create, larger structures. We're finally assembling Lego pieces. So the compound has characteristics that are different from those of the elements it's formed from. So if you have carbon and a hydrogen and an oxygen and you bring them together, it's going to form a compound made of these 3, but that compound will be different. Its property will be different from carbon by itself or oxygen by itself or hydrogen by itself. This is the example here of sodium by itself is actually a metal. It's a solid metal. Chlorine by itself is a gas, a yellow gas, if you have chlorine by itself. Sodium by itself, if you add water on it, is actually going to explode and react with it. But if you add sodium and chlorine together, sodium the metal with chlorine the gas, and you add them together, it forms salt. That's it. Salt, the table salt that you put on your food. So you see that salt is a compound that has completely different properties than sodium by itself or chlorine by itself. So some elements are essential because of, so I really should have put this slide as well earlier because I already talked about that. This is an example of how iodine is one of those trace elements. So this wasn't in the previous slide that I showed you about trace elements. It just wrote, it was just written, trace elements are also important, and it's part of those, 25 total. Yeah, let's go back to that one. Right here, this one. 25 essential elements, and trace elements was at the bottom representing 0.01%. So now And I should have moved that slide sooner, this one here, because the trace elements here, it's kind of blown up and you can actually see what does that mean, trace elements? Trace elements, we're talking about boron, chromium, copper, fluorine for your teeth, iodine is for your thyroid, iron in your blood, manganese. So all of these, selenium is for the brain. All of these are important for physiological functioning, proper physiological functioning of your human body, but in very, 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 very small amounts. And this is an example of how iodine, which is right here, you see iodine. Iodine is part of those trace elements that we need. If we have an iodine deficiency, our thyroid is going to blow up and we're going to have thyroid issues. Because thyroid hormone happens to be made with iodine. So you'll learn that in a different course, in an anatomy and physiology course. You'll talk about the iodine in the hormones T3 and T4, the hormones that are produced by thyroid hormone, by the thyroid gland, and these require iodine. So if you don't have iodine, you can't produce these hormones, and then you have a disorder. So radioactive isotopes can help or harm. So sometimes we use them to our advantage to kind of look at things in the body. So we use kind of non-harmful radioisotopes, of course, and some of them are harmful, and they're used in, for example, weapons, like radioactive, the nuclear bomb. Or they're used for generation of power in nuclear plants. And again, I probably should have put that particular slide when I was talking about radioactive isotopes, but that's okay. So some of this radioactivity can actually be used to treat certain cancers. We use radiation to kill cancer cells, especially, for example, in prostate cancer, which is actually a cancer that is treatable. It's not as dangerous as some other cancers, like pancreatic cancers is very, very dangerous. But prostate cancer is treatable. And the way we do it is we literally kind of inject pellets of radioactive iodine literally in the prostate gland. This is kind of the procedure that we do, where we literally with a needle, we just kind of like inject radioactive seeds to, as they're emitting radioactivity, they kill the cancer cells and we cure prostate cancer like that. This is just an example at the end here. Okay, that's it. That is it about atoms and elements, and hopefully you understand the subatomic particles and how we deal with the electrons on the electron shells. It's very, very important. I'll see you in the next chapter. Bye-bye.